example. Did we go over this?
I don't think so. No, because last time our notes stopped like at the example just before this one.
Oh. Okay. Then hold on a second. All right. So this is where we are at. All right. I gotcha. All right. So we are at example 2 here. Okay. And we're talking about entropy. S delta S. So I want you to associate this with disorder. Okay, disorder. Okay. Things can move towards disorder. Okay, so what does disorder mean to you? Okay. Disorder here in thermodynamics means entropy. All right, so disorder. Again, I'll ask you the same question. What does disorder mean to you? Probably for us, from a chemist perspective, more space, more mass, and definitely more motion. Okay, more motion, more kinetic energy, things moving around. All of these types of phenomena lend to more disorder. Okay. Okay, and we assign that an entropy of positive. S, which is entropy, can be standalone. But a lot of times in thermo, we do change in entropy. And if it contributes towards more disorder, that's a positive sign. Okay? If some reaction contributes to more order, that is a negative sign. We tend to say that entropy and change in entropy being positive, this is a spontaneous process. I'll just put spontaneous here. Think of putting a piece of iron out, whether it's a day, 2 days, or 2 decades, or 200 years, that iron will rust. Okay, it will oxidize. And that is a spontaneous process. Without our intervention, without us doing anything, that iron will rust. If you take ice, okay, and leave it out, okay, without any intervention, okay, it will melt, okay, provided the temperature is, facilitates that. Delta S negative or S negative, this is a non-spontaneous process. Okay, like I said, this leads to more order. Okay, so you have to put in the work. Okay, you have to put in the energy. Speaking of work, there's an equation I'd like for you to know. It's delta G equals delta H minus T delta S. Right, so you'll learn a lot about this if you take a thermodynamics class. Maybe they talk about it a little bit in biochemistry or biological chemistry. But this delta G is Gibbs free energy. And it is energy that allows us to do work, not heat, work. Okay, work is good energy. Okay, like moving a cell or twitching a muscle or actin or whatever for all of you biology majors. Okay, it takes energy to do that. So a directed energy. This is not energy that just goes away like heat. It goes into the atmosphere. Okay, or it just goes away, dissipates. So we say Gibbs free energy is energy to do work. Okay. And if this is negative, this is an exergonic process. And And that means, yes, okay, we will go to products. Okay, the products are favored. And if it's endergonic, you have to put in the work. Some external source of energy is required, and it will go to the reactants. So this is the final judge. This determines everything. This delta G determines everything. But notice this delta G is going to take input from enthalpy, and it's going to take input from entropy. And let's just go over quickly what enthalpy is. Okay, we may remember from Chem 1 that enthalpy is a heat flow. This is heat. Okay. Some reactions produce heat, and we call that an exergonic reaction, exothermic reaction. Exothermic, literally the surroundings get hot. And then the enthalpy delta H, if it's positive, it requires heat, or it takes in heat from the surroundings. This is an endothermic reaction. Alright, so there's a, yeah, okay. So I'll highlight here, if a reaction, it has a negative enthalpy, positive entropy. Okay, let's plug it into this equation. A positive value makes this negative. A negative value makes this negative. So negative already into negative makes it negative. So these are reactions that is both enthalpically favorable, entropically favorable. The reaction is going to occur. Okay, and it really doesn't matter what temperature it is at. Okay, so if your delta H is negative, your delta S is positive. Okay, a positive delta S makes that negative. The negative delta H makes it negative, 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 negative. This whole delta G will be negative, regardless of whatever temperature. That reaction is enthalpically favorable and entropically favorable. Okay, let's do the flip side. I'll highlight this in pink. Okay, let's say a reaction is endothermic, positive, okay, requires heat. Let's say the reaction is negative in terms of entropy. Negative means more order. You have to make order happen. So a negative into a negative is a positive. Positive plus a positive enthalpy. This is going to be positive no matter what, regardless of temperature. So we have reactions that is enthalpically disfavorable and entropically disfavorable. That's in the pink.
So endothermic would equate and endogonic would
an endothermic plus non-spontaneous will be endergonic no matter what temperature. That's the right way to say it. You're right.
So it's endogonic plus what?
If your enthalpy is positive, if your entropy is negative, you plug a positive here, Bailey, you plug in a negative here. No matter what, this will always be positive. And if delta G is positive, we know that the reaction is not going to favor the products. Now, the situation is if you're like yellow and pink, or pink and yellow, then you worry about the temperature. Then temperature plays a role. Okay, if you're pink and yellow, or yellow and pink. Okay. All right, let's go to this diagram here. This is where we left off. All right, so we have 2-iodine solid going to 2I gas. So what would you predict the delta S will be? Because here in this question we're asking for the entropy change, and entropy change is delta S. So from a solid we're going to a gas.
What disorders?
or disorder, so positive. Okay. All right, here we have 2 solids plus 1 gas going to 2 solids. Okay, so if you break apart this equation, we have a solid, which is very ordered, going to another solid, but we have a gas also going to a solid. We have 3 moles going to 2 moles. So we're making a solid, so this is more order. And the correct answer here is that delta S is negative. I'm not going to ask you this on the exam, but if you have this gas, this is a gas, right?
Yeah, all 3 of them are gases.
All 3 of them are gases, but we have 2 gases, 1 plus 1 is 2, going to 2 gases. So 2 gases going to 2 gases, this is no change, or I don't know what ambivalent, or undetermined, I would say. Okay, why did I say you can't say positive or negative? Because you have 2 gases going to 2 gases. There's no change. Okay, there's really no change in order or disorder. So you may encounter that in your future chemistry classes. For now, I will not ask you this on the exam. Okay, but just want to tell you that some chemistry textbooks are very tricky. Okay, very mean. I'll just quickly skim over this before we go to some practice problems. So the entropy of the universe increases. Okay, so the universe we're talking about always increases. Okay, this is very interesting. There's like books on this, like library books you can read for fun, talking about increasing entropy. So we take the surroundings and the system and make that the universe. If it's an equilibrium process, all of this is equal to 0. Okay, so there's no exchange between the system and the surroundings. Okay, if you're in equilibrium. All right. So all of this is called the second law of thermodynamics. I will not ask you the second law, or I don't even know what the first law is, to be honest. And then there's a third law, but I will not ask you this, but I just want you to know, just for your own information. Okay. All right, we'll have some problems on the exam that utilize this equation, the change in entropy. Okay, change in entropy. And it's this equation here. Okay, you're going to take the sum of the products, okay, minus the sum of the reactants. Okay, sum of the products minus the sum of the reactants. Anybody know what this N and M are? Okay, this N and M are what are known as the coefficients, okay, stoichiometric coefficients. So we always balance our equation. All right. And does anybody know what this little O means? It's called not. And that means standard state. Standard state. So this is the change in the entropy of the reaction under standard state conditions. All right, so we'll utilize this equation. We'll do this problem here. So standard state, you'll get these values, okay? You'll get these values on the exam. You can look them up in the back of a textbook, do people use textbooks these days. You can look them up in the back of your textbook. I'm sure you can find the tables of these online. All right. So let's predict and calculate the standard entropy change for the following reactions. Now, to do this problem, we'll have to refer to page 5 of our notes. Okay, page 5 of our notes, because I got these values from a textbook. Okay, these values. So these are standard entropy of formation values. Just bringing your attention to the units. Nothing more, nothing less. Okay, just look at the units here for entropy. All right. Okay, first thing we'll do is predict. Okay, let's predict this, and then we'll put it into this equation. All right, so we have 2 gas plus 1 gas, so we have a total of 3 gases going to 2 gases. So do you think this delta S will be positive or negative? Okay. We have 3 gases going to 2 gases. So what do you guys think? More disorder or more order? Okay, more order, that is correct. So more order actually means that the delta S is going to be negative. All right, let's really see if the delta S is negative by plugging in real numbers. All right, sum of the products minus sum of the reactants. Okay, sum of the products minus sum of the reactants. So our first product is CO2 gas. And what is the standard entropy of formation for CO2 gas? So everyone look at me here. Okay, CO2 gas is 213.7. Okay, 213.7. That's for 1 mole. But how many moles do we have in the problem? So we have to multiply this by 2. Okay? So don't forget to do that on your quiz or your exam. Okay? This is a common mistake. Okay, minus, I want you to put a big bracket because this is products minus reactants. Let's do CO. This is carbon monoxide. And CO is 197.7. That's for 1 mole. But how many moles do we have? 2. So we'll do 2 times 197.9 plus, okay, plus, what do we have to plus? The value for oxygen. So what is oxygen? Oxygen gas is 205.0. That's for 1 mole. How many moles do we have? 1. 205.0. All right, do we know how to do this on our calculator? This is the second source of mistakes I see students do. And it's probably just inadvertent, because sometimes this happens. One thing is, I want everyone to look at me. This minus, okay, distributes. It distributes. Okay, so it's minus 2 times this, and minus into plus is? Minus into plus is minus. Okay, so there's many ways we can solve for it. Okay, you can do it 1 step, you do it multiple steps. Okay, 2 times 213.7 minus 2 times 197.9. Okay, minus into plus is what? Minus 205.0. Minus 205.0. Getting minus 173.47 joules over mole Kelvin. Okay, we predicted it to be minus, and it is minus. Okay, see? We predicted this to be minus, and it is minus. Okay, we predicted it to be minus because it's going towards more order. 3 moles of gas to 2 moles of gas. So this is how we do these types of problems. Let's go on to a couple more here. What do you predict? The delta S. 3 moles of gas, O2 going to 2 moles of gas. Okay, 3 moles of gas going to 2 moles of gas. I'm predicting it to be negative, right? 3 moles of gas going to 2 moles of gas. That is more order. Okay, more order, less disorder. So let's look up O3 now. O3 is 238.8. That's for how many moles? That's for 1 mole. How many moles do we have in the problem? 2. So we'll multiply this by 2. Okay, want to put a big minus sign here. Sum of the products minus sum of the reactants. Let's look up oxygen gas, its standard entropy of formation, and that is 205. That's for 1 mole. How many moles do we have? 3. Okay, are we comfortable doing this on a calculator? Yes or no? Okay, the answer is yes. If we're comfortable doing this on the calculator, I got an answer of minus 137.45. Okay, so make sure you get that. And look, we predicted this to be negative, and it truly is negative. Why? We have 3 moles of a gas going to 2 moles of a gas. That is more order, less disorder. All right, our last one here, let's predict. What would you predict this to be? Okay, we got a solid going to a solid, but look, we have a solid going to a solid, liquid, and gas. Solid being transformed into a solid, liquid, and gas. So what do you think the delta S is going to be for this, or what would you predict it to be? Okay, we predict this to be positive. Let's figure out the numbers here. Standard state, CO2 is 213.7. Okay, that's for 1 mole. How many moles do we have? 1. We have H2O liquid. Okay, 69.9. That's for 1 mole. How many moles do we have? 1. We're balanced, right? Make sure we're balanced. Yeah, I think we're balanced. Sodium carbonate, Na2CO3, 136. That's for 1 mole. How many moles do we have? 1. Okay, I want you to put a big minus sign here. And actually what I really want you to do is put a really big bracket here. Okay, a big bracket, because that's minus the reactants. We have 1 reactant, that's sodium hydrogen carbonate. Solid is 102.1. That's for 1 mole. How many moles do we have? 2. So we got to multiply this by 2. Okay, are you guys comfortable doing this on a calculator? Yes or no? If you are, make sure you check your answer with mine. I got 215.3, or somewhere around that number. And look, we predicted this to be positive, and it indeed is positive. Just in the interest of time, I'll have you look at this on your own. It's relating to the entropy of the surroundings. It's equal to the enthalpy of the system. Okay, what is the system? It's the actual reaction, not the test tube, not the beaker, okay, just everything inside of that. Okay, the enthalpy of the system minus that divided by the temperature is equal to the entropy of the surroundings. What is the surroundings? It's the beaker, it's the test tube, okay, it's the room, it's the universe, okay? So take a look at that. You can read this on your own, and okay, do that for your studying, especially if you're going to major, or if you're a science major, chemistry major. Just in the interest of time, I'll focus on other things here. So let's go to page 6. Here's another thing I'll just let you guys read, and just, it's not something I'm going to test you on, but it's just some good information to have, especially if you are a science major or a STEM major. The third law is that the entropy of a pure crystalline substance is 0 at absolute 0. Okay, absolute 0 is 0 Kelvin. Okay, 0 Kelvin. So the idea is very interesting here. The idea is the most ordered substance is actually a crystal. Okay, it's anybody heard of X-ray crystallography and the famous Rosalind Franklin's diffraction pattern of DNA? Maybe have you heard of this? Okay, so DNA is they crystallized it. Okay, you want to get really, really good crystals, and you can hit it with X-rays and you can get the structure. Okay? But for a crystal, in terms of entropy, it's very, very ordered. And if you can get the temperature to 0 Kelvin, everything is still. I believe this is impossible, but I'm not sure. Okay, I believe it's hard. But if you can get 0 Kelvin and you're a crystal, they say molecular motion ceases. Okay, everything ceases, and if that's the situation, your entropy is 0. Okay. I think before we were saying how the entropy of the universe always increases, and entropy tends towards more disorder. But if you're a crystal, which is the most ordered, more ordered than a solid, and you happen to get the temperature low enough, absolute 0 Kelvin, you can get the entropy to be 0. Okay, and that's the third law of thermodynamics. All right, we will continue now to the last bits and pieces here. Gibbs free energy. Okay, so this is it. Okay, this is the one that really decides whether a reaction moves towards products or not. Okay. It takes input from entropy and enthalpy. All right. We can also say Gibbs free energy is the energy available to do work. And we have the exact same reaction as we did for entropy. All right, sum of the products minus sum of the reactants, exactly the same. All right. Question is, what about the sign? Okay. If your delta G is negative, the reaction is going to favor the products. We call this an exergonic reaction, okay, like we've mentioned before. Favors products. If your delta G is positive, the reaction is non-spontaneous. Okay, it favors the reactants. We call that an endergonic reaction. You have to put in the work to make the reaction go to products. If your delta G is equal to 0, then there's no change. It does not favor reactants or products. All right. One thing here, bringing your attention, this is standard state. Standard state. So we have delta G of the reaction at standard state. Oh, we can just have plain old delta G in any conditions that are not standard state. Any conditions that are not standard state. So just be able to discriminate and recognize what is standard state conditions versus any conditions, any temperature, sorry. That not means standard state conditions. These are non-standard state conditions. Let's go quickly to page 7. This is the exact same situation as delta S, same equation. Page 7. All right, let's look at this table one more time. If your delta H is H enthalpy, delta H enthalpy is negative, it's entropically favorable. If your delta S entropy is positive, that's spontaneous, more disorder, that is entropically favorable. If you plug those negative and positive values in, you'll always get a negative delta G. Negative delta G means it favors the products. Okay, so we have something that's enthalpically favorable, entropically favorable. The reaction is going to go to the products. Okay, the flip side. Okay, something that is enthalpically, let's go to the second one here. Something that's enthalpically favorable, enthalpically not favorable, that's an endergonic reaction. And entropically not favorable, that is non-spontaneous. It will always be positive if you plug that into the delta G. So regardless of temperature, it will never go to products. All right, let's say something is enthalpically not favorable, but entropically favorable. Okay. Endothermic reaction, enthalpically not favorable, entropically more disorder, favorable. So what do? Okay, you raise the temperature to make it spontaneous. Okay, so if you have a delta H that's positive, a delta S that's positive, just raise the temperature T, making this more negative. If you make that more negative, the delta G becomes more negative. All right, let's look at the flip side here. If your delta H is negative, that is an exothermic reaction. Your delta S is negative, that is something that's not favorable. That's more order. That doesn't happen spontaneously. What do you have to do? You got to lower the temperature to make the reaction go to products. Okay, so you imagine in red here, your delta H is negative, your delta S is negative. Okay, to make this negative more negative, you'll lower the temperature. Okay, so that's this scenario here. Okay. All right, so yeah. All right, so the bottom one, enthalpically favorable, exothermic, negative. entropically not favorable, more order, lower the temperature to make it happen. Put a negative in here, put a negative in here, make this temperature as low as possible to make this negative and the overall delta G negative. All right, so make sure you know this fairly well. And now it's time for some equations that I will give you on the exam. It's 10-12. All right, so we have here delta G. Is this standard state or non-standard state? Okay, non-standard state plus equals delta G standard state plus RT natural log of Q. Okay, Q. So what is Q? Q is called the reaction quotient, and we use Q to compare it to K. Okay. All right, so what I usually tell students is I put Q first and then compare it to K, K being the equilibrium constant. All right, if Q is greater than K, okay, the reaction will favor the reactants. Okay, so the reaction favors the reactant side. If Q is equal to K, it doesn't favor anything. Okay, so we actually say if Q is equal to K, that is what we're going to say is in equilibrium. It does not shift anywhere. And then finally, if Q is less than K, the alligator jaws point to the product side, and this reaction favors the products. So those are the scenarios that come from this equation. Okay, by the way, I'll give you R in the RT natural log of Q. R is 8.314 joules over Kelvin mole. I'll give you that. Okay, I'll give you that constant. Okay, notice to get the delta G of non-standard state, what do you need? What do you need to calculate delta G at non-standard state? You need the delta G at the standard state. Okay, did you notice this? Right, hopefully everything comes together now, chapter 17 and with chapter 16 and 15. K is your equilibrium constant. If it's large, imagine if I gave you $1 million, are you moving forward or backward? Okay, most people are moving forward, so that's a large K, though K has no units. So if the equilibrium constant is large, the natural log of K is positive, but plugging it into this equation is negative, so the products are formed. Okay. By the way, here's another equation I'll give you on the exam. Okay. A delta G standard state is minus RT natural log of K. So what's the difference between this equation and that? And what's the equation between this and this? Standard state. Okay, so here delta G is minus RT natural log of K. Okay, we replace Q with K, which means we are at equilibrium. And what else happens? This delta G becomes 0. So when you plug in your delta G is equal to 0 here, delta G naught is minus RT natural log of K. We replace Q with K. Why? Because we are at equilibrium. If you're not at equilibrium, the reaction is going to move till it gets to equilibrium. Well, I'm going to give you these two equations, so just so you know. Okay, one is where will it shift to get to equilibrium? And the other one is, you're already at equilibrium, what is the delta G at standard state? All right, if your K is very, very small, you favor the reactants. The natural log of K is negative. Plugging that in, the delta G standard state is positive. Reactants are favored. And in this scenario, if the delta G is equal to 1, that means K is 0, and your delta G is 0. Remember, K equal to 1, it's not favored reactants or products. Okay, that's a delta G not of 0. Alright, so let's do a problem here to make this more sense for us. Like I said, I'll give you these two equations on the exam. Alright, the last two problems, and then we'll move on to the final chapter in Gen Chem 2. And that is electrochemistry. All right, calculate the equilibrium constant Kp for this reaction. So here's our reaction. And it's asking for the equilibrium constant. So, and Kp, the P stands for pressure. And I'm going to use this equation here, okay, that I will give you on the exam. Okay, delta G naught is equal to minus RT natural log of K. Why am I using this? Because I have the delta G standard state values for each of these elements. All right. So how will I get to delta? So this is the equation I'm going to use from our notes. How will I calculate delta G? Okay, it's sum of the products minus sum of the reactants. Okay, sum of the products. So we have O2, sum of the products. So O2 is 0, and that's for 1 mole, but we have 3 moles, so it's going to be 3 times 0 kilojoules per mole. Okay, minus, I want you to put a big bracket here. Okay, minus sum of the reactants. The reactants is O3, and it's at 163.6. That's for 1 mole, but how many moles do we have here? 2. Okay, sum of the reactants minus sum of the products. So I'm going to just go ahead and give you that answer. I'm getting minus 327.2 kilojoules per mole. Okay, minus that. So I have a question for the class. Is this exergonic or endergonic at standard state? It's negative. So if it's negative, it is an exergonic reaction. Will it generate energy? Yes. Will it favor products? Yes. Okay, yes. Okay, how do I know this? It's negative. Okay, will this release energy that could be utilized for other purposes, whatever it may be? Yes. Okay. Favors products at standard state. All right, we have that delta G of the reaction. Let's plug that in here. And then solve for K. All right, I'm going to put this to joules per mole, okay? Okay, equals minus R, which is minus 8.314 joules per mole Kelvin. T, what is T here? T is temperature. The temperature here is 25 degrees. Let's convert that to Kelvin. Okay. And convert converting that to Kelvin is going to be 298 Kelvin. Okay, natural log of K. All right, so K has no units, so I'm just going to put in the numbers here. That equals natural log of K. Okay, do we know how to solve for K? Okay, it's the inverse natural log. Okay, the inverse natural log. And the inverse natural log is E. So it's going to be e to the power of whatever all of this is. So when I do this on my calculator, let's just do it on our calculator. Okay, so the minus minus cancels. Okay, divided by 8.314 times 298. I'm getting 132.065. So e to the power of 132.065 should give you my answer. Okay, it's going to be shift natural log 2.26 times 10 to the 57. That's huge. This favors the products immensely. 10 to the 57. It's crazy. Sorry. So notice this favors the products, right? It's huge, definitely. Okay, and what else? Okay, in terms of products over reactants, this favors the products tremendously. 10 to the power over 57 is way all the way forward. But in terms of energy, in terms of thermodynamics, which is the point of this chapter, it also tells us it favors the products by the negative delta G. So they corroborate one another. And now let's do our final problem before we finish the chapter. All right, the Kp for this reaction, okay, we are at an equilibrium here, is 4.3 times 10 to the minus 4 at 375 degrees C. In one experiment, the initial pressures are pressure of H 2.4 atmospheres, pressure of N 2.686 atmospheres, and pressure of NH3 4.4 times 10 to the minus 3 atmospheres. Calculate delta G for the reaction and predict the direction of the reaction. So we want to calculate delta G. Okay, are we at standard state? Okay, if we're at standard state, this would be 1 atmosphere. But are we at 1 atmosphere? No. Okay, one of them is at 0.4, one is at 0.86, the other one is at that. So standard state, 1 atmosphere. This is not standard state. So what we will use is this equation here. Okay. So let's calculate Q here. Q is going to be products over reactants. These are pressures, so it's going to be the pressure of NH3. Okay, we will square this. Yes. Divided by the pressure of N2 times the pressure of H2. We will cube this. Okay. Okay, the pressure of NH3 is 4.4 times 10 to the minus 3. Okay, there's no units, so I'm going to not put units. There's no units in K or Q or pH, POH. Divided by pressure of N2 0.86. And then pressure of H2 cubed is 0.4 cubed. So what do we do when we get this on our calculator? What's the answer? So I am getting, let's just do it together here. 4.4 times 10 to the minus 3 squared. Okay, divided by 0.4 cubed. I'll just do this. Okay, 0.4 times 0.4 times 0.86. Close those parentheses in the denominator. I'm getting 3.52 times 10 to the minus 4. So this is Q, and our K is 4.3 times 10 to the minus 4. And then our Q is 3.5 times 10 to the minus 4. It looks like this one is favoring the products, okay, under these conditions. Okay, under these conditions, it's favoring the products. Okay, so under these non-standard state conditions, favoring the products. Okay, so we have our Q here. Okay. So we got our Q, we have R, we have T, and now we need to calculate delta G naught. This is products minus the reactants, some of the products minus some of the reactants. So let's do that quickly here. Okay, so we're going to calculate delta G naught for this reaction. Okay, we have NH3 gas. That's for 1 mole, and that's minus 16.3 kilojoules per mole. Okay, that's for 1 mole, but how many moles do we have? 2. Okay, minus, okay, I want you to put a big bracket here, some of the products minus some of the reactants. We have N2 here, and that's at 0 kilojoules per mole. And then we have H2 here. This is for 1 mole, but how many moles do we have? 3. All right. Okay. All right, so what's 2 times minus 16.3? It's going to be minus 32.6 kilojoules per mole. Okay, minus 0 and 0 makes it 0. And I'm going to go ahead and convert that to joules per mole. And that is minus 32,600 joules per mole. All right, so now we have delta G of the reaction. And then we have Q here. Let's plug everything together. Okay, by the way, under standard state conditions, this would be exergonic. Under standard state conditions, this would be exergonic. So now we have delta G is equal to minus 32,600 joules per mole plus R. I'll give you R. R is 8.314 joules per mole Kelvin. Okay, T here is 375 degrees C. What's 375 degrees C plus 273? Okay, 648 Kelvin. And natural log of Q. What is natural log of Q? 3.5 times 10 to the minus 4. And this will give us our final answer. So, we know how to do this on our calculator. Natural log of 3.5 times 10 to the minus 4. Times 648 times 8.314 minus 42,871. Okay, I'll just write that down here. Okay, by the way, the kelvins cancel, so we're left with joules over mole. And then minus 32,100 here, or minus 32,600 here. Right, so minus 32,600 minus 42,871 should give us our final answer. And I'm getting about minus 75,440. Minus 75,470. Okay. So this is our answer. Okay, I can divide it by 1,000. I'll get minus 75.5 kilojoules per mole. Okay, either or is the right answer. So what do we see here under these conditions, under this temperature? A standard state is 25 degrees. This is not standard state. It's a very high temperature. Under this non-standard state temperature, under these non-standard state pressures, standard state pressure is 1 atmosphere. This is exergonic. Okay, exergonic. Under these reaction conditions. So this is our answer. All right. So I'll give you this equation on the exam, and yeah. Okay. So this is for the non-standard state. Any temperature, any reaction, any pressure, any concentration. This is for standard state, 25 degrees C, 1 molar concentration, 1 atm pressure. All right, so that is a wrap of this chapter here. And then we have one more chapter to go, which is chapter 18, which is electrochemistry. Debating whether I should continue or call it a class. We have 8 Are there any questions or comments here? All right, let me just give you a brief introduction. Let me just take 5 minutes or so, and then we'll go over our last chapter. Your lab, our final lab of the semester also, is on this stuff. So let's do this thing here. All right, another thing I'd like to mention, now would be a good time to turn in your, I do not know the due date, to be honest, so don't email me about due dates or ask me, but if you're, as we approach the end of the semester, turn in your Chapter 17, upload it, and then I'll give you 10 points for that so that we are on pace here. All right, so Chapter 18 here is on electrochemistry. Have you guys heard of a battery? Okay, batteries. Okay, so a battery contains two parts. It contains a cathode and it contains an anode. Okay, so really in electrochemistry, what we're talking about here is using some chemicals to make a battery. And a battery is usually measured its power, its energy, this is not a physics class, but usually we measure the power of a battery with voltage, volts. Okay, battery has volts, okay? 9-volt battery, 12-volt battery, however many volt battery. So can we make a battery out of our chemistry reagents? Okay, that is the whole idea behind electrochemistry. It's a mashup of the words electricity and chemistry. Okay. So a battery contains two parts. One is a cathode and the other one is an anode. So this is how I know what happens and what doesn't happen. What happens in a cathode is reduction. Okay. Oops, sorry. Red cat eats an ox. That's what it is. Red cat eats an ox. Okay, red cat eats an ox. Okay. So reduction occurs at the cathode. Reduction occurs at a cathode. So what is reduction? Okay, any reduction in a battery is gaining of electrons. Okay, gaining of electrons. All right, so here we're going to say electrons as E. E minus or 2E minus. Okay, or gaining of electrons. Okay, anode is a site of oxidation. This is a loss of electrons. Again, an electron can be E minus, 2E minus, 3E minus. Okay, so reduction and oxidation combined together is an oxidation-reduction reaction, also known as a redox reaction. Okay, a redox reaction. Okay, so this is a couple. A redox couple. Okay, so I'll end this class with an example. So let's say me and Bailey are a redox couple. Okay, we are a couple that's in redox. That means we transfer electrons. Okay, for every giver of electrons, there's a taker. Electrons, not protons. This is not acid-base. electrons. All right, so let's say I give 1 electron. We'll do a 1 electron transfer reaction. I give 1 electron to Bailey. Okay, I give 1 electron to Bailey. There's my 1 electron. Okay, there it is, E minus. This is a 1 electron transfer reaction. Okay, who takes that electron? Bailey, because in this example we are a redox couple. Bailey is going to take that electron. Bailey, right? Bailey. And when she takes that electron, she becomes Bailey minus. When I give up that electron, I become VJ plus. Okay? So when we add these two reactions together, I, as VJ, lose 1 electron. So I become oxidized. See that? The electron that's lost is liberated in the product side. Okay, Bailey gains that 1 electron. She becomes reduced. Okay. So we can't have half reactions. Okay, first of all, we can't have free electrons. Okay, no free electrons. They're actually bad for you. Okay, so we add the oxidation and the reduction reaction. We get the full redox reaction. And when we do that, this is what we get. Okay, this and this cancels, and we get Bailey plus VJ. Okay, Bailey takes that electron. She becomes Bailey minus. And she took it, I gave away that electron, I become VJ plus. Okay, so this is the full redox reaction. Okay. Who gets oxidized and who gets reduced? I, as VJ, lose 1 electron. I get oxidized. And if we are a battery, I am the anode. So this is the oxidation half reaction. This is the anode. And what is Bailey? She gains electrons. She becomes the cathode. And she is reduced. Okay? So Bailey is a reduction half reaction. I am an oxidation half reaction. We join us together, we add them up, we cancel out electrons, we become a redox reaction. Okay, so now we will replace VJ and Bailey with actual chemicals. We'll attach some voltages to them. Okay? Remember, a positive voltage. All our batteries are positive. So students do not understand why students don't understand this. If you're a positive, the reaction is favoring the product side. That's a positive voltage. Okay? Negative voltage, you're just a dead battery. All right, I will see you all on Tuesday. We will try and finish this chapter up, and then once we finish this chapter, we are done with the class.